can't wait to finish my talk so I can eat it. So my name is Kevin Xu. I work for a company called PingCAP, which is a company behind an open source database that's really popular called TiDB. And today, though, I'm actually going to talk more about Kubernetes and operators. So before we start, has anyone heard of Kubernetes before? Raise your hand. Very trendy crowd. What about the operator pattern within the Kubernetes world? Okay, a few more. Sounds good. What about TiDB, the open source NewSQL database, which is open source? Okay, a few more over there. All right, so I will do my best to put all that actually into one deck, one presentation together, so they will all make sense, those three things, as we talk about our use of operator in the Kubernetes world to run TiDB, which is a NewSQL database, really well in the cloud. All right, so as I advance this, so that is basically an agenda for today. Quick history and walkthrough of TiDB. I'm going to do a technical walkthrough, and the walkthrough will actually be relevant to how we're doing operator stuff in Kubernetes, and then ultimately walk through how we're actually doing the operator pattern to run a cloud-native stateful application, which of course a database is. A quick recap about PingCAP, the company. It was founded roughly almost 4 years ago now by 3 infrastructure engineers who were making an open source database called TiDB. Ti just stands for titanium. It is a MySQL-Compatible NewSQL database, meaning it's a relational database that actually scales very well horizontally, just like a NoSQL database that many of you are familiar with out there. And we have offices throughout China, throughout North America. I'm the person actually leading our US-based operation here, and I drive a lot of our cloud strategy, which ends up being a lot of Kubernetes, as you might imagine. So here's a quick community recap. So we have 2 main repos. One is called TiDB, one is called TiKV, which is a key value store. I'll explain what all that means in a little bit. But we're actually one of the most popular database products or projects on GitHub right now. Over combined 20,000 stars, more than several hundred contributors at this point. And earlier this year, we held our first user conference in Beijing. We had over 700 people come, all developers, users, practitioners. So I'm very excited about that progress. And there's a bunch of companies actually using TiDB in production right now, from big telecom companies to food delivery. Some of these companies are based in India, based in Singapore, obviously US-based companies as well. And we're also in a core banking use case in the Bank of Beijing, which, as many of you know, is a very high standard for database transactions and so on and so forth. So this is kind of the current update on where TiDB, the product, is. And the key main use cases are twofold. Because we are a MySQL-compatible database that scales horizontally, usually the 2 pain points that we solve is when your MySQL single server is getting too big and you're thinking about potentially manually sharding your database, which is how a lot of companies are currently scaling as their database grows too big. TiDB actually scales automatically for you, and you don't have to manage all that manual scaling policy. And another use case is that if you're already sharding your MySQL, but you're sharding it along one dimension usually, and you want to do analysis on another dimension, say sharded on user ID, but you want to analyze on hotel ID, for example, if you're like a 2-sided marketplace, TiDB actually supports that very natively without you having to manage a ETL process to pipe it to a different data warehouse, so on and so forth. This is just a really brief overview. We're happy to talk to any of you guys more detail after the talk about how these use cases are actually being deployed in all these companies. This is just one example I want to highlight. The company Mobike is one of the world's largest stockless bike sharing platform. You probably see a lot of similar companies here now in the form of scooters, like Lime or Bird. It's essentially the same thing with a different kind of transportation vehicle. And Mobike is actually one of the first companies that pioneered this model, and they're all over the world. This is a picture I snapped in Cologne, Germany, when I gave this talk about a month and a half ago at a Kubernetes meetup in Cologne, of all places, and I saw our users, actually with their product in the wild. So, quick technical walkthrough of TiDB. Like I mentioned, it's a NewSQL database that speaks MySQL. It is a strongly consistent database, so it has ACID guarantees, and its technical inspiration actually came from the Google Spanner project. Many of you might have heard. It's actually also a product now inside Google Cloud. And what's interesting is that with our architecture, we separate the SQL processing layer from the storage layer so that you can scale basically your compute resource and your storage resource independently of each other. And I will show an architecture diagram in just a little bit to see how that works. And with this kind of pluggable modular architecture, you can plug a bunch of different things on top of it too. So we actually have a Spark connector where you can run analytical jobs much more quicker in the same system. So in a way, we're actually a system that supports both transactions and analytical processing in the same platform. So this is kind of what it looks like. On the top, you have this thing called TiDB, which is just the SQL processing layer that speaks MySQL. And one thing I want to note here is that this is not a MySQL fork. We actually architected this whole layer from scratch, so our compatibility is by default not 100%, but we made that choice so it can be optimized to work much better in a distributed storage setting, which is ultimately what this thing sits on, so that it can get better performance with a bunch of storage nodes on the bottom. And this layer is actually stateless, so you can run this all in memory. They're almost more akin to a microservice in a way. You can spin up a bunch of TiDB nodes if you have a lot of computing traffic coming in, a lot of write traffic, for example, and then destroy them when, say, your shopping promotion campaign ends. And underneath it, you have a bunch of nodes called TiKV. KV just stands for key value. This is where all the data is actually persisted. So this is the storage layer. And as you can tell, these two things are separate, so we can scale them independently of each other, depending on your use case and your resource needs, which is a very cloud-native way of actually consuming technology. And how we do replication and scaling is that we break up all the data into smaller chunks that we just happen to call region within our own documentation. These are key value pairs that are ordered by their byte array, so you can do range scan and other kinds of operation along these data. And they're replicated automatically using the Raft consensus protocol, which is a fairly popular now consensus algorithm to achieve consistency. And I won't go too much detail into Raft. Obviously, I have to talk about it offline. But how it works at a very high level is that it replicates your data into 3 different copies, or 5 or 7, but basically odd number copies. And they will vote on a leader, and the leader will serve traffic, both read and write, while the other are automatically there as backup for high availability purposes. So that's on a very high level how Raft works. Underneath each TiKV node, we also have an instance of RocksDB, which is a very solid storage engine that is open source and maintained by Facebook. So underneath each thing, you can see a little RocksDB, RocksDB, RocksDB. And this capacity can be scaled in either direction, so horizontally, if you have a lot of data that you want to store in the system. And another component up here is called PD. PD just stands for placement driver. You can think of it as a metadata cluster that keeps all the metadata about TiKV, and actually does a lot of work in terms of automatic balancing your data. Say if you add a new node over here, the system can push additional data to the new node, balance the work traffic, remove hotspots, things like that. So it's structurally it's akin to like a zookeeper, and it's also highly available. That's why we have 3 different nodes, and they're also replicated using the Raft consensus protocol. So I know that was kind of super quick, but all this actually will matter when we talk about the operator in a little bit. And just a quick more newsy level update from our side. Earlier this year, we announced a kind of a newer initiative that we call TiFlash. As some of you may come from, a more columnar background, you know that this is still a key value store. So if you do a lot of analysis, it's still relatively slow, and we understand that. So we've been working on a column-based store where you can basically make an extra copy from your Raft consensus to come to this side, for example, and sits on top of the column store. And then you can actually do analysis at the same time without any ETL process. And your data is both consistent and available to you in real time. So you can really query fresh, transactional data with really, really good performance, and then we put our TiSpark plugin on top of it. So this is something to look forward to. But as you can see, a lot of components going on, right? So why are we invested in the Kubernetes operator? That's the reason. So I'm going to try to explain Kubernetes on one slide, but really it's just the stuff that's relevant for this particular talk. There is a bunch of stuff on Kubernetes. It is a very fast evolving, I will call it a set of APIs. Some people like to call it a cloud operating system almost, but it's really taking off. It's really converging around this set of open source APIs that was used in Google Inside for a long time before they open sourced a few years ago. But at a very high level, there are three things that I want to make sure everyone kind of knows terminology-wise. One is just the word pod, which is the smallest unit of work that exists in the Kubernetes world. It's basically just like a node or an instance. It can hold a container, or it can hold more than one container. But the point of it is that it's relatively kind of ephemeral in the sense that if it just kind of crashes and dies, it just dies. It doesn't really matter. Just get a new pod. And it's kind of this paradigm shift of a cattle versus a pet. I don't want to offend anyone who worked on a farm and worked with a lot of cattle, but kind of the analogy here is that you don't really care about a cattle when it dies, but when you're a pet, you want to take care of it. It's very high maintenance. This pod requires a lot of work, but the pod kind of way of thinking about it, or container for that matter, lets you be very freed up in terms of your resource usage and also kind of the way you decompose everything into your microservice. And there are two important APIs that kind of goes along. There are actually a bunch of them, but the two I want to mention today is one is called deployment, which is the API for a pod that is used very widely now to run stateless applications. So the TiDB server that I was talking about before, just the SQL layer, the MySQL protocol that routes out your SQL query traffic, that is stateless. So you can probably actually just use deployment for that kind of workload. You can declare a number of replicas, do rolling deployment, updates, and things like that. But of course, we are a database company. As you know, we have the KV layer on the bottom. It has to maintain state, otherwise your data is going to get all screwed up and your users are not going to be happy. And there's another API called stateful set. And this is designed to actually help you run stateful applications in the Kubernetes kind of environment. So what it does is it actually maintains order of different pods as they go, gets deployed. And this is very relevant for TiDB. It maintains what is called a sticky identity. So each pod, when it's working with stateful set, actually will have a network interface and a storage interface that's sticky. That's always with this one pod. It never goes away and gives it to another pod. And then you can actually interchange the pods either as it gets matched up to a specific storage unit, for example, where your state is maintained, literally where your files or data is stored. So that's what this API does. All right? So Kubernetes on one side. Okay? And this is an example of what these APIs actually looks like, which is really just a YAML file at the end of the day. This is a stateful set. Literally on the very top, I can you can probably see it. There's just this attribute called kind. It says stateful set. That makes it a stateful set. If it says deployment, that makes it a deployment. If it says something else, that makes it something else. And you can actually specify this into all kinds of different levels of abstraction, and we are doing that with our own operator, which I will show you. But in this stateful set example, which runs Elasticsearch, you can specify a bunch of stuff. And what's really important probably is on the bottom is you can specify your resources, right? Like for each pod, how much CPU do you want it to be? What is the limit of it? What are you requesting? What is the memory request? All these kind of resources will really matter as you run different components in the cloud. And a quick history of operator itself being a pattern. So it was actually pioneered by the folks at CoreOS, which got bought by Red Hat, which got bought by IBM. So now it's actually like a technically an IBM thing now. The framework was introduced back in 2016. That's when we as a company first started picking it up and started playing around with ourselves. And now Red Hat actually is pushing this thing called the operator framework to make operators super easy for you to do. So you can literally make an operator about something, just as soon as you go home, and then it'll probably work, hopefully. We started working on our operator back in 2017. So we didn't actually take in much of what the operator framework does. So there's a lot of difference in here. And I think the Red Hat folks recently launched the operator hub.io, which is a collection of a bunch of operators. So you guys can check out all the operators that are out there currently. And I think ours will be up there soon as well. And the reason why we care about this pattern is that there's a bunch of reasons, and these are, kind of the rundown of the features that we like to ultimately be able to encode into this pattern, so you, as the end user of this database in the cloud, don't actually have to deal with a lot of the very important but typically very routine operational tasks that you have to do when you operate a database. It's almost like an extension of your SRET using software. So things like scaling, things like doing rolling updates or doing backup and doing recovery and accessing different kinds of cloud storage for different kind of performance requirements that you need. All this stuff you can actually encode in the operator. So is the promise. And ultimately, what's really interesting for us is that you can enable this multi-cloud way of deploying very easily, as long as you have Kubernetes in your cloud environment, whether it's public or private in your own data center, which seems to be more and more the case these days. You can run your operator in any of these environments, and then you can have this like meta multi-cloud cluster of your data, regardless of whether you want to use AWS or GCP or something else, or probably a little bit of both. And why should you care? Well, if you are potentially the end user of something like this in the cloud, like I mentioned, using something with an operator could really drive down your operational costs by quite a bit if you want to run different kind of stateful applications specifically. Not so much for stateless applications, like I mentioned. The operator is really geared towards running stateful applications in the cloud, whether it's database or caching or monitoring. It can be extension of your team, and it's also gaining a lot of popularity in the database community for this very reason. At a very high level though, operator, all it does is it measures up or it matches up the resources that you, the user, want each of your database components to have. You have a controller in the middle that matches up with your actual cluster so that all these things are in sync constantly. And as you change your resources, you update them, your cluster should know and update that at the same time, but still maintain the state. And the one component that you might see a lot of in the operator world, if you dig into some of the code, is this thing called CRD, which stands for Custom Resource Definition. It really is also just a YAML file. It's a big list. It gives you it lets the end user specify all the resources that you want for each of your pod, each of your components, and then it gets deployed into your cluster via the operator. And there's also another way in the Kubernetes world called API aggregation, but it's actually supposed to be a lot more powerful, but a lot less supported at the moment. So right now we're using CRD. A lot of people are using CRD, but I do want to mention this in case you guys are interested in digging further into this API aggregation, which you can find in the Kubernetes documentation as well. So back to stateful set. As I mentioned, we use stateful set a lot as the API to help our pod maintain its order and its uniqueness. In the TiDB context, the way you deploy a TiDB cluster with all the stuff that I just mentioned to you is that you actually deploy the PD, the metadata layer first, which kind of makes sense. You want to make sure that the guys that's tracking everything gets deployed first. And then you deploy TiKV, the storage layer. And then you deploy TiDB, the SQL layer, the stateless layer on the top. And that's the proper order to deploy a TiDB cluster in production. And that's why order matters a lot. And also, each of the pod basically is a TiDB pod, or a TiKV pod, or a PD pod. And they're all unique, right? They have unique identity, they have unique jobs within the ecosystem, and they also require different kinds of resources to do their job well. So they need to have a sticky identity to make sure their network identity is the same and their storage identity is the same. And you can't really interchange some of these things as you have them in production, right? Of course, something is going to die. Something always dies. And you want to be able to map that to the same, what is called volume, which is kind of this, term that basically has all the information that keeps the state to the same pod so that your state is maintained in this constantly kind of changing and very flexible and fluid cloud world. And this API, stateful set, wasn't stable actually until Kubernetes 1.9, which wasn't that long ago. And we're now at 1.10. 1.14, which was yesterday. And that's why there was a quote around smooth operator at the very beginning of my intro slide, because this has been a really interesting journey, actually making all this work really well. But with all the stateful set, what we did was we made a custom controller in the middle. We asked our users, usually provided by the user, a CRD of things that they want to have or things we recommend that they have when they deploy TiDB in production. And then you maintain your cluster state over here. What that looks like in real life looks more like this, where on the side, what we did was that we actually made another abstraction layer on top of the stateful set and the deployment. We call it TiDB cluster. So like I said, the kind, you can call it anything you want if you want to make more abstractions on top of it. And then underneath it, with the CRD, what you do is that you have a PD pod, right? You have an image. You specify the number of replicas, which, like I mentioned, is 3 by default. And then you request very little memory and CPU because it's just a metadata layer. And then you have your TiKV. You know, this is abbreviated, but you definitely have a lot more CPU and a lot more storage request resources over here. And then see TiKV, you know, you can have it all here. So you can specify as many TiKV, TiDB, PD as you want, and it's all kept together very simply and very nicely for you, so that all the components that you're looking at actually isn't that complicated to deploy or run or manage at all. But like I said, the smooth thing is a work in progress. This is Kubernetes 1.14, and something we are really excited about is this persistent local volume being GA'd, meaning that we can have this API. There's another API called persistent volume claim inside Kubernetes that lets you really reliably access local storage in a cloud environment, which to a database could mean huge performance differences between a network storage and a local storage. And if you look a little bit closely, this thing just got announced yesterday. So if I gave this talk last week, I wouldn't even be able to say that this is something that we can use in our operator or anybody's operator. But with that being said, everything that we're doing in our operator is open source. You just Google TiDB operator, you'll find it. I suggest you use the user guide within our docs if you want to deploy it on any of these platforms, you know, just for fun, or maybe in your production as well. And you can also do the same on Google Cloud's marketplace. We have an operator that's just there for you to use in the marketplace. It's still 2.0. Our software is actually at 2.1 now, so we should probably update this soon. But you can actually run this very easily using your $300 free credit if you've never used GCP before. You can look at all the deployment as well in terms of how the different components work, what resources are being deployed, why, so on and so forth, which is a really great way to learn about our operator without having to do a whole lot of work. And last but not least, just want to share another reason why we use the operator, and we're working so hard on it, is this TiDB as a service offering, which is similar to like a Mongo Atlas, for example, where you can really just use this entire thing as a service, as an end user, and most of the stuff's all managed for you. I would say the operator probably gets you like 75–80% there, but there's a lot of other things that we have packaged around the operator. But having the operator as a core, so you can very easily consume this database product with just like an API exposed to you that your application can talk to, and then you just, you know, go on your way and keep on building your business however you want. And if you guys want to check it out, you know, you can go to our website and just, you know, put in your name and I'll give you early access or something. Okay? So that, I kind of blew through a lot of things, not just because I want to eat dinner, but thank you for your time. But I'm happy to take questions for roughly 4.5 minutes. Yes?
Yeah, so you mentioned the resources for the different components, which immediately brings to mind. What sort of observability do you have for tracking the behavior of different components? And the other is auto-scaling. Are you able to like auto-scale the TiDB?
Yeah, TiDB or TiKV. Yeah. So first question is observability, right? So one thing I omitted intentionally is that every time you deploy TiDB, we deploy Prometheus as our metric database by default to track all the stats that is in your cluster. to observe, and then we expose it into your Grafana dashboard, which is another popular open source dashboard. You can see everything. Those are actually two more components that if you dig into your operator, you see, oh, there's another pod that's for Prometheus or Grafana. So that's like the default option for you to observe any TiDB cluster. That's just kind of like there for you. And the second question about auto-scaling is that, yes, but the reason we haven't done it is because at least our philosophy or our experience is that it's actually good to give your user some control or knowledge over scaling before they scale, because what you end up happening is that you set a policy, all right, we can scale TiKV cluster when CPU usage hits 75%, and then boom, it just does it. And then you forget that you even did this. You come back with, why is our bill so high? We could probably get a little bit more out of the remaining 25%. So from a feature or a technical perspective, it's not terribly hard to do, at least in terms of scaling out. But from kind of a user experience, you usually want to talk to a user before you make sure you're cool with auto scaling, right? Because you're the ones actually paying the resources at the end of the day. And another component to that is, because of our architecture, you have the storage and the compute on 2 different layers. You can scale in and out, which is kind of nice. The only caveat is that for your storage layer, without your state being maintained, when you scale in, you want to make sure all your data is actually backed up, or you know that they're going to get deleted and you're okay with it before you start to reduce your storage resource to save money or whatever. And that, if you make it automatic, could get you in a lot of trouble that you didn't foresee before. So we're just being kind of careful, with that feature. But yes, with a but. Anything else? Yes?
What kind of local storage, persistent storage do you need? SSDs or?
Yes, yeah. So we always recommend SSDs for the TiKV nodes. For the TiDB nodes, it doesn't really matter because they're mostly in memory, kind of just services anyways. Yes, but for local storage, or even for the network storage, you can probably, depending on which kind of cloud platform you use, right, they're like network SSDs, or they're local SSDs. But their performance actually vary quite a bit. Some of our experience have been that local SSDs of certain cloud actually is slower than network SSD, which makes no sense. So that's like another thing that we're investigating, which is very cloud dependent. But yes, SSD in general is what we completely recommend to get the most out of something like this.
And would you like to share any benchmark details, like how many queries per second and what are the...
Yeah, no, absolutely. I can send you a few links of our latest benchmark, which is all public on our GitHub repo. I just have to dig it up for you. Our being a distributed database, I would say generally speaking, what you look for is kind of the balance between your latency and your throughput. Being that if we're never gonna be as fast as a single server, database, even like MySQL, for example, because we're by definition distributed, right? But of course, we have the scalability, we have the throughput in there, and what we try to achieve in our performance in general is that as you scale your TiDB cluster, you can handle way more traffic, and your latency is more or less flat, right? You can maintain that performance and that speed as your capacity grows. So happy to share more, afterwards. Anybody else before I get replaced? Just like a pod.
Yeah, so one question here is that your equivalent of the YAML file,
yeah.
So you specify the memory and CPU. So how dynamically you can change that?
You can change that fairly easily, honestly, and that's kind of what the operator is supposed to do for you, right? The controller in the middle.
So what does it do? It restarts your container. What does it do?
So what it does is that it actually kind of changes the provisioning of the resource on the bottom without having to change anything in terms of the service itself.
Kubernetes
Exactly, right. So that's what kind of the persistent volume claim API is supposed to help you do, is to fetch new resources, right? And as you update that, which generally speaking, you probably don't do a whole lot in practice. Like you don't do that like every 2 weeks or something. It's almost usually like initially you want to specify what you need to do. Yeah, cool. All right, well, I'm around if you guys have more questions.
Thank you, Kevin. Next we have Denis Magda, VP of Product at GridGain, PMC Chair at Apache Ignite. And by the way, GridGain is sponsoring tonight's food and raffle, so you guys don't miss your chance to win a PlayStation and a Casio watch with calculator. So register for the raffle over there at the counter, and we'll do the drawing at the end of the evening. Right, Dennis?
All right, wonderful. Thanks for coming, everyone. The next topic, it will be a Swift one, the first presentation, but now we'll talk about another database-like technology, memory computing platform, Apache Ignite and GridGain, and how you can use this technology for your real-time Node.js application. By the way, before we start, anybody uses Node.js? All right, a couple of, yeah. This presentation will be for you guys. I'm working for you today. Wonderful. So let's talk about the agenda. First of all, I want to answer a question. Why Apache Ignite and Node.js? What's the problem? After that, we'll quickly jump to the Apache Ignite overview meaningful for Node.js deployments. And after that, I'll show some of the quick demos so that if you're curious, you can come home, pull out your laptop and create a quick cluster, deploy your first Node.js application and get it up and running in 5 minutes. And after that, I'll quickly jump to the implementation details for those who are always want to get to the bottom of how things work. And finally, just some of the ideas of how we as Apache Ignite community and I as a GridGain product manager see the future of this client. So let's start with the simple question. Why to use Node.js with Apache Ignite? So those of you who already use Node.js in your daily routines and from day to day know that Node.js is best suited for real-time applications. Whenever you want to get the fastest response time, or whenever you want to handle your events in the fastest manner, Node.js is pretty good framework and programming language. For sure, it has some of the architectural specificities which might be seen as limitations for languages like Java or .NET, but generally speaking, I would say that this concept when the whole engine is single-threaded is not that a big deal. Whenever you're just focused on the purpose of your technology, such as fast real-time processing, like big throughput, etc. And this single-threaded approach allows us to use to turn your Node.js applications into prudent ones, those who would utilize all of your CPU and memory resources in the most efficient way. And basically, that's how you're just getting flooded by a lot of queries and events coming to your application, and you can just quickly, one by one, get them done. For sure, here is Node.js imposes some of the limitations and discourages us to use and run long-running computations, but instead you can use the framework for the purpose it was designed for. Apache Ignite, if to try to build the relation between Node.js and Apache Ignite is designed to solve performance and scalability problems. Whenever you want to get an ultra-fast distributed memory-centric storage, or you have any bottlenecks with your relational database, or your Hadoop cluster cannot, complete your queries in milliseconds, and it does this all the time in minutes, then you can think about Apache Ignite. If to quickly make an overview of Apache Ignite, how many of you guys heard about this technology before? All right, yeah, a few hands. So generally speaking, this slide it's like a building block, but whenever I am presenting Apache Ignite to the guys, I'm usually saying that generally speaking, it consists of two primary components. The first component is a memory-centric storage. So we can store data in a distributed way in memory and on disk. And on top of the storage, we have the second component, which is just basically a set of the APIs available and well integrated, tightly coupled with this memory architecture. So when we talk about persistence options, here is we can think of two primary use cases for Apache Ignite. The first one is your existing database acceleration. Let's say you have Postgres or MySQL and you want to make them faster, you want to make them scalable, and what you can do, you can deploy Ignite on top of your Postgres database, switch your applications to Apache Ignite, and that's how you can get the benefits of in-memory computing, and you offloaded your relational database. Basically, why this is doable, right? Why Ignite can offload or accelerate the relational databases, because the APIs we support SQL, we support transactions, we do key value, you can run MapReduce like computations, etc., etc. So pretty straightforward. Another option is our native persistence, which is also distributed. Let's say that you have some bottlenecks with your Hadoop cluster. For instance, some of the operations have to be executed in seconds or milliseconds rather than in minutes. You take this subset, put in our cluster, we store it in memory on a disk across a cluster of machines, and now you have your applications who are doing some complex analytics with Hadoop and real-time analytics or calculation with Apache Ignite. That's another approach how you can utilize this memory configuration. These building blocks to the right and to the left is what GridGain as a company adds on top of Apache Ignite. Everything here is open source, available for Apache Ignite community. And here is we have things like memory and monitoring, security, data center replication, blah, 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 which goes in our enterprise editions. All right, problem is clear. We completed our standard marketing presentation. Now let's get to the technical details. So before we talk about the usage of Node.js together with Apache Ignite, let's briefly check how Apache Ignite cluster gets assembled and deployed. Generally speaking, when we talk about Apache Ignite, we have server nodes. And your server node acts as a container for your data and computations. So whenever we talk about the cluster or distributed database, etc., that's something united. And that's a union of your server nodes in case of Apache Ignite, which in fact will store your data evenly across a cluster of machines, on-premise, in the cloud, Kubernetes, etc. You choose your deployment option. And then we have our applications, right, which like to make use of your cluster. And in case of Node.js applications, we supported a set of their APIs available for Apache Ignite. Not the whole list of the APIs, as you would see going forward, but at least something meaningful for their specificities of Node.js, which is designed for real-time applications, for fast response time. And Node.js client is pretty simple and pretty straightforward. So from the implementation standpoint, it will be connecting to your cluster via TCP/IP protocol. So it will, whenever you will start your application, you will pass your IP address of one of your server nodes of your distributed database, and that server node will serve as a proxy for this client application. And once you get connected, after that, you can use the following APIs. Key value calls, when you know a primary key, the fastest way to look up data in a distributed database. Then we have SQL, and you can also scan through your data. And for sure, you can, if you're starting from scratch, you can configure your data model, your caches and tables in Ignite statically using configuration prepared for your server nodes, or you can do this dynamically later. When you created your applications, you start your application and you create your tables, etc. later on. And before we switch to the first set of examples, if to talk about SQL APIs, which are important for those, let's say we have our Node.js applications, and now we decided to accelerate MySQL database, how would I switch my Node.js application to Apache Ignite cluster? And Apache Ignite cluster will still have your MySQL database as persistence layer for the sake of durability. But what should I do? Generally speaking, first of all, you will be required to adopt some of the best practices and changes related to your data model. So whenever we talk about distributed databases, we have to consider so-called like affinity collocation, data collocation. Whenever you have your related data, like organization and employees, and you are storing your data in such a way that all of the employees of a specific organization are located on the same cluster node. This data layout helps us to run SQL queries with joins, aggregations, if much more efficient. But from the syntax standpoint, there is nothing extraordinary, like selects, different functions. We support NC99 specification. And as for the data will sit in memory, it will sit on disk, etc. And you will be able to query your data sets this way. So let's quickly jump to the code samples, because I want to show how it's quick, even for first comers to Apache Ignite to start with this product. First of all, whenever we are talking about a distributed cluster, it doesn't mean that you have to provision anything in your environment or in the cloud. You as a developer can start on your local laptop, because yes, you're given a task. You want to implement some Node.js application. Why would I go and negotiate with someone, some infrastructure hardware? I have my laptop. So what I already did as prerequisite during the preparations is I downloaded Apache Ignite from their website. And here is how do I start my first Apache Ignite node. I can leverage from this Ignite SH script, which goes in the distribution. So what we do is we execute the script on my local laptop, and in a couple of seconds I should have my first server node up and running. Right, so it's over here. We have our cluster started. Right now I have just one node, but it's already available for our needs. Let's boot another one. We just repeat the same procedure. I'm starting my cluster node, and now both nodes will auto-discover each other through TCP/IP connection. All right, so I have a cluster, a true cluster, two cluster nodes, two servers, which will act as my storage and my compute nodes. Next step, let's just create a Node.js application. I'm a lazy guy, so I decided, to go ahead and download as part of the same package. Apache Ignite community provides some basic Node.js samples. So what I did, I created a project in WebStorm. That's a development environment. Let me quickly check how can I increase the font size, but yeah, I can't find a control. All right, anyway. So this project, what goes inside? Some of the simple samples like key value samples, SQL samples, etc. Let's start with the simplest one. So here is, that's how Node.js client looks like. So I already have all of those libraries needed, bundled as part of this project. That's how I connect to the cluster using this IP address, and I know that one of the server nodes, which are already running, will be listening on this port number, so I'll be connecting to one of the servers. Pretty straightforward. Once I connect it to the cluster, I'll create some objects, I'll create a cache. A cache is the same thing as a table in the relation of vault, just logical place where we store our data. We create our cache, new cache, and after that we are putting some data into the cluster and we are getting it back. If we jump to the implementation, how it looks like, we create person object, we put this person in the cache, and then we are getting it back. Pretty trivial. So let's just launch this application. All right. So we executed this application. We see that we could successfully connect to the cluster. Everything is up and running. And also at the same time, as a developer, sometimes I'd like to observe what's going on with my even local cluster. Memory utilization, CPU utilization, etc. To do that, again, I'm a lazy guy. So I'm using Web Console. I know that you can deploy your Web Console on your premises. I usually go to console.gridgain.com. I have my account there. And now, before this presentation, now my cluster is attached to to my account on the console.gridgain.com. And what I can do is I can go to the monitoring tab in here. So nothing, and like I've just opened this page, so there are no any metrics usage. Yes, some heap usage is recorded, but generally here is my 2 nodes, some memory related information, and a cache which was created by my application. Just for entries were added to this cache. But at least I can go ahead and do some of their monitoring tasks with this. If you want to check any SQL example, it's all the same. Here is, you have a choice of using just SQL language. Again, we will connect to our cluster through Node.js client. Then we will create a table, country, we will create elbow city, we can use this syntax, DDL. And then they will be running we can create secondary indexes if you want to traverse our data much faster, not just through scans. And some sample dummy data like cities, countries, etc. Let's just execute this code sample. Alright, so we inserted cities, we found out the most populated cities in the world, such as Shanghai, Moscow, if to believe to this sample data set. If you jump back to our metrics, we can see here some of the changes in our cache size. Yeah, it grew because we created another table, another cache, and now we have more entries in our cluster, in our local cluster. What else can you do with this monitoring tab? If you want to experiment with some of the SQL queries, you don't need to code them. You can go to our queries tab. And here is I have some of the predefined queries for this specific domain model. For instance, now I'll run this. I'm trying to find the most populated countries in the world. I connect it to my cluster, and the top 3 countries are China, United States, and Russian Federation, if to believe to this data set. Just that's how fast your kind of getting started can be with Node.js and Apache Ignite. Just download the binary, start your first cluster locally, and run your first code samples. Then go ahead and modify your code depending on your needs. And also you can monitor what's going on with your local cluster. Finally, going back to our slides, what else is left? So that's the primary information. My goal was to show you that if you use Apache Ignite as a memory computing platform to accelerate your MySQL databases, to offload your Hadoop deployments, or just you are using it as your memory-centric storage, then you as a Node.js developer have the APIs needed to have your applications migrated to Apache Ignite. Now quickly, if to talk about the implementation details, these thin client APIs, right? They are implemented on top of our socket level binary protocol. That's a special cross-platform protocol which was supported for Apache Ignite, I think 1 release ago. And on top of this protocol, now we can enable as many programming languages as we like. Because before we had this protocol, we supported only 3 programming languages: Java, .NET, and C++. And those languages were integrated natively. Even Node.js and C++ applications were required to start JVM process internally because of the way how that native integration works. Right now, you as .NET, C++, Node.js, Python, or any other programming language developer don't need, to be worried that your language will not be supported. We have that low-level socket protocol, and it's all about, implementation details, just to provide a high-level API on top of this socket-level protocol for your favorite programming language. That's what we did for Node.js. And presently, Apache Ignite provides thin clients, lightweight clients, for the following programming languages out of the box, and we know that there are some of the other community initiatives when developers and engineers supporting languages like Go, etc., and they are not part of their Apache Ignite standard distribution. So we have Node.js, Python, PHP, Java, etc. And I'll have this slide, I'll quickly show this slide because we have all of those standard clients in Apache Ignite like Java, C++, and in .NET. And we only have now a set of thin clients, lightweight clients. What are the pros and cons? I don't want to list everything, but generally speaking, from the scalability and performance standpoint, right now, if you wanna, when you are connecting through Node.js client as one of the thin clients, that client will be working through one of your server nodes, and that server node will serve as your proxy. So whenever your application issues a request, I want to get this data or that data, all of the requests will first come to that node, and after that, that node will decide who is the primary owner of that data. And it will redirect the query, and also it will get result set first back and forward it to you. That's not good from the performance standpoint, and we don't have such a gap for our standard clients, which can locally find out who are data owners, and they can connect to a specific server node to fulfill your request. But also right now, we are working, that's like the limitation of the present. But right now, the community has been working on their direct communication enablement for the thin clients. So we are supporting so-called partition awareness protocol, when even your Node.js applications locally will be able to go to a server node, which is the primary for an entry or record. That's what we are doing right now. It's already kind of done. We just need to prepare it for the release. But what would be then, if we talk about the rest of the differences, then how do I choose? If I'm a Node.js developer, then I don't have a choice. I always will be using the thin client. But what if I am a Java developer? Here is your checklist. Thin clients support these APIs for now only, like key value lookups, SQL, scans, and configuration, while standard clients do everything available in the platform, such as compute grid, machine learning, streaming, etc., etc. We are thinking that many of these APIs going forward will be supported for the thin clients such as Node.js in the future, like an ability to trigger compute tasks. Like, let's say that you created some complex code, this code is deployed on your server side and you want to execute it. We will give this way to you on Node.js side. Continuous queries, that's a way to listen for the changes, updates happening on your storage side, so that, for instance, some data has changed and you have some applications listening to those events, we want to act on this information. But also, the primary source of input is our users and our customers, etc. Give a try and let us know what's missing, what's meaningful. Finally, this presentation will be shared, so if you want drill down to the details, here is where you can read more about Node.js, another getting started guide. Also, if you want to see what are the steps to do to, let's say, take my existing MySQL database and to accelerate it with Apache Ignite and then connect from my Node.js applications, check out this nicely written blog post. And also, if you have any questions, go to Ignite community, and you also can try GridGain community edition. So we GridGainers, right, we're one of the contributors to Apache Ignite, but at the same time we provide our own source available GridGain Community Edition, which you can use free of charge. And why would you use it is if you want to get bug fixes, some improvements, etc. ahead of time. Something that is not available in Apache Ignite yet, or something that might not be available in Apache Ignite in general. And also, final slide is if you decide to use Apache Ignite and you need any support for your Apache Ignite deployments, etc., you can go to GridGain and we will be able to help you, because we know Apache Ignite, we develop it, we create it, etc. Any questions? All right. Yeah, please.
So on the JavaScript support, is it only Node, or can you use a web browser, say, through WebSockets?
You mean like from the application standpoint?
Yeah.
Yeah, absolutely. So your application can be deployed in a web server whenever you like. It can be mobile application, it can be a web application, etc. The whole point is that if that's a web application, yeah, you just take this API and you're connecting like you would connect, let's say, to a MySQL database or anywhere else.
Over HTTP or a WebSocket, or you have to go through the...
In this way we use internally. You will be providing us a TCP IP address, like an IP address of one of your server nodes, which are deployed somewhere, port number, which is the default one, which is predefined, and that's it. Also, for the sake of fault tolerance and high availability, you can enlist all of the IP addresses of all of your server nodes, because what might happen is that some of the server nodes goes down, and the client internally will be able to reconnect to the rest of the cluster nodes. I think, yeah, from your standpoint, you're just taking this library, and internally we are just opening one IP port number. Once we release that direct communication or partition awareness, then the client internally will be opening socket connections to the other server nodes. It still will be connecting first through a proxy, one of the servers, but then it will receive all of the information needed from the proxy server to be able to connect to the rest of the cluster transparently. All right, we are done. Thanks a lot, and
Thanks, Dennis. Last but not least, Doug Hood here from Oracle TimesTen Scaleout. Doug will tell us about how to scale non-trivial applications, and we'll do the Raffle afterwards.
Okay, smile everybody. So what I'm going to be talking about today is scaling non-trivial applications in distributed databases. It's really easy to scale trivial apps. It's quite hard to scale non-trivial apps. So I think it's quite good timing that I went after Kevin, because everything Kevin said I 100% agree with. How distributed databases work, how Kubernetes works, how operators works, we're totally on board with that. One comment Kevin made is a difference. Kevin was saying that they don't try and be faster than a single database because it's a distributed database, there's network hops. With my product, we do try and be faster. And if we're not faster, we get unhappy, because we believe you can get higher throughput, higher availability, and flat out go faster if you do have many machines. It's easy to say, it's really hard to do engineering-wise. So I'm going to go through some examples, and what I encourage is questions. Technically, I write C code for a living, but I spend a lot of my time talking to people. If I say the same thing over, I get bored. You'll probably get bored listening to me lecture to you. I don't want to lecture to you. I want to throw some ideas out. I want you to challenge those ideas. Is that right? What about this? What about this case? That way, hopefully, I can learn something and you'll be more interested. So I want to go through some really basic stuff, latency, throughput, scalability. Look at how that applies to some trivial benchmarks, which is what a lot of database people talk about. Because trivial things are easy. They're easy to do, easy to get good results, so people show those results. But I then want to contrast that with, I'm deploying this technology with large customers that you've heard of, and they're doing really gnarly stuff. I want to see some of the challenges we had with that and some of the techniques and approaches that we did to apply it. Because I think a lot of the techniques and approaches are independent of the database technology. In theory, they can be applied to many different things. So hopefully it might be useful to you guys. And as I said, please ask questions as we go. So first of all, just some definitions. Whenever I talk about performance, people go, yeah, I know all about performance. But weirdly, a lot of people get confused between latency, throughput, and scalability. Latency is how long an individual operation takes. The faster you do that individual operation, the better. If you have a single connection and you have really low latency, the reciprocal of that latency is the throughput. If you have multiple connections, you get more throughput than that. So the point is, if you have low latency, that really helps. If you have high latency, it's a challenge to get high throughput because you're going to need many connections to do that. Scalability is another concept. It's basically how much throughput can you get when you add more resources to a system. It's intuitive, you just add more and it will scale linearly. That's the theory. In practice, it's a lot harder than that. The real world gets in the road. Okay, so any questions on that? Right. So here's just some examples of latency. So first of all, how many of you use SQL? Okay, so I'm talking about SQL selects and update statements in a relational database. If you do primary key lookups with an index, it's probably as fast as it's going to get. So in this example of latency using my product, which is an in-memory product, which is why we're talking about this in-memory Meetup, we can do those things pretty fast. We can do a SQL select in under 2 microseconds on, quite frankly, 5-year-old technology until Broadwell technologies going at CPU going at 2.2 gigahertz. So that's reasonably fast. An update takes longer. Because you're doing an ACID transaction, you might need to roll back that transaction. So you need to know the prior information. So there's more going on, so it takes a bit longer. So that's about 5 microseconds. So the latency for trivial operations can be fast. If you're doing a join of 20 tables with nested subselects, it's going to take longer. But the point is the really basic operations can be pretty fast. Any questions on that? Okay. Now we look at throughput. The examples I'm using, so how many of you guys have heard of Apache Cassandra? Okay, MongoDB, Scaleout, it's a C++ version of Apache, VaultDB, okay, Aerospike. Okay, so the point is, these are popular distributed scale-out technologies. They do similar but different things. They have different sweet spots. They're good at different things. But at the end of the day, they're all databases. And one way that you can differentiate databases, should I use this one or that one, is you compare performance. So what most databases do is they compare throughput. And they use a benchmark called the Yahoo Cloud Serving Benchmark. Many years ago, Yahoo had a bunch of use cases. They had some technologies they want to compare. Should I use technology A or technology B? They looked at their critical workloads and said, this particular workload is read intensive, that one's write intensive. They looked at what their workloads were and they applied it to various NoSQL technologies. So that benchmark became popular, they open sourced it, so a lot of databases compare that. So if you dumb it down, the throughput, the operations per second, bigger is better. So the operations per seconds, not transactions per second, because quite frankly, they're not really ACID transactions. They're mostly singleton operations with eventual consistency. So I'm calling them operations rather than transactions because I have a very specific definition of what an ACID transaction is. These are not ACID transactions. So the point is, the bigger the better. So Cassandra, great technology, scales really well. The more nodes you add, the faster it goes. But each node doesn't tend to go that fast. So for this particular workload, 32 nodes, you've got the slowest number. You know, Mongo went faster with less machines. Great for that workload. It turns out, off these published benchmarks, so if I hover over them, if you Google it, who the vendor is, has published their own benchmark. So I literally look at the internet, see what numbers are published. It turns out that Aerospike came up with the biggest number. It was slightly bigger than VoltDB just because of a rounding up. So the point being, simple workload defined by an independent party, the bigger the better. You can use any hardware you want. You can use as many nodes as you want. So these are the published numbers. You might have your own numbers, but at the end of the day, what are you comparing against? What credibility do you have? These are the published numbers. So the thing to remember, the biggest number, 1.6 million. So this is throughput, number of operations per second. So using my database, TimesTen Scaleout, using 2 nodes, 2 machines, we're doing 2.7 million, whatever those things are. So it's faster than the fastest Aerospike. They used 8 nodes, we used 2 nodes. So that's throughput. That's a good number. This histogram gets higher. What does that mean? This is about scalability. With 2 nodes, we do 2.7 million whatevers. With 4 nodes, we go faster. So as we add more nodes, we get more throughput. So this is an example of scalability. Okay? So the point being, there's lots of technologies out there. You guys seem to be familiar with a lot of these. This technology has low latency, has high throughput, and it scales. And it appears to be far more scalable than the other databases. So there's a data point. But this, in my opinion, is irrelevant because this is a trivial workload. Logically, it's one table, you're hitting one row, and you're doing a read or an update. It's trivial. If you're Yahoo and Yahoo email's not doing very complicated things, maybe you can break it down to these atomic operations. So if you're doing trivial things, great, we scale really well. Most of my enterprise customers don't do trivial things. They do nasty things. They do evil things. They do really complicated things. They're not dealing with one table and one row for operations. They've got many tables. They're doing joins. They're doing nested subselects. It's just really complicated. Complicated things take longer to do. The latency increases. As a consequence, the throughput isn't as great and the scalability can suffer. So I'm trying to look at real-world complicated systems and how to scale those instead of trivial things like that. So that's an example of some trivial stuff. Here's another example. Different workload. We're doing 153 million whatevers. One table, hitting one row. 153 million, whatever. That's worth 20% updates. If you do 100% updates, 1.4 million whatevers. It's trivial. Big number, but it's trivial. So what do we run it on? We ran it on a pizza box. The 2-socket Intel thing happens to be an Oracle Sun box, but if it was a Dell box or a Levino box or an HP box, it's going to do the same thing. It just happens to run on the Oracle Cloud, and we were using local storage. Kevin was talking about that. Totally believe in local storage. If you're doing scale out and you write to a local device, the I/O on your local device is not affecting anyone else. If you're scaling out and you're all writing to a shared device, if the aggregate write rate that all the nodes are doing going to that shared device is more than that device can handle, that's called a bottleneck. So we were using local storage, it was local NVMe, so it's pretty good hardware. So local storage for scalability is great. It costs more, but it's independent, therefore it will scale. The worst case is when you're doing shared storage over the network. Okay, any questions on this stuff? So the point is, it's a pizza box, pretty cheap, we use 64 of them. So what I'm talking about, I'm not really going to talk about the product too much. I'm going to talk about how we scale things, because I believe it's kind of independent of the technology. The point is, TimesTen Scaleout, it's a single database, but it runs on many machines. The fact that it runs on many machines, we try and make transparent or hidden to you, because you shouldn't need to know. The more nodes you add, the more throughput, the better the high availability, the bigger the capacity. Okay. So, the customer I've been working with, so first of all, question, how many of you are Luddites? Does anyone know what a Luddite is? Yep, excellent. For those that don't know, Luddites are people that don't like technology and don't want to use it. Okay, so none of you are Luddites. Therefore, probably half of you in this room are customers of this customer. You are their customer. I'm not going to say who it is because it's a Fight Club thing. Any of you guys familiar with Fight Club? Really? Okay, what's the first rule of Fight Club? Yeah, so the point is, this is a big customer, this is their internal IP, so I'm not saying who they are or what they're doing, and I've changed the table names because they don't really want to make this public. But the point is, you're probably one of their customers. You probably use this technology every day. So the point being, they've got a really complicated data model. I'm just looking at a very small subset of it. Not sure how good you are with colours. Sort of the light green 4 tables at the top are involved in one of the queries I'm dealing with. The bluey thing's another query, the slightly darker green's another query. So what I'm going to be talking about is a data model with a bunch of different hierarchies, so you've got to do a bunch of different joins. So for this customer's workload, they had 2 workloads. They had what they call a read workload, which is dealing with this thing, and they have a write workload, which I'm going to cover in a bit. So the point is, it's not a single table, you have to do joins. And by the way, each of these tables has hundreds of millions of rows. Okay, so remember, there's the light green, the slightly darker green, and the blue. So there's logically 3 different things happening. And I've tried to map it to what we've got here. For the lighter green, we're doing a 4-table join. And this weird thing with the plus, that's the Oracle syntax for a left-outer join. It'll also work with ANSI syntax. I just happen to be more familiar with the Oracle syntax. So you're doing a 4-table join that includes a left-outer join. So it's a join, and that just happens to return a result set with 1 row. The output of that, there's lots of columns selected, but the output is the input to the next query. That's trivial. You're doing looking at 1 table, looking at 2 different predicates, 2 different columns. The output of that goes to another table. You do a query, there's a bunch of different bind variables, and that returns a result set on average with 17 rows. It may return thousands of rows, but on average, it's going to be about 17 rows. So, pick your favorite database technology. This first query on the top left, you're joining 4 tables, there's hundreds of millions of rows in each table, and we've got a left-outer join. Give me a guess on how long that's going to take. This is latency for a single connection. A guess. It's random. Give me a guess.
3 seconds.
3 seconds. Can anyone beat 3 seconds? What was that? Give me another number.
300 milliseconds.
300 milliseconds, that's a good number. Do you think you can go faster than that? So remember, when you do a single operation with a single connection, how long that takes is the latency. The reciprocal of that will be the throughput for a single connection. When you want to maximize throughput, you have more connections. So the faster you can make this, the more throughput you can have. But just here's another fact. When I worked with this customer, they said, this is the thing you've got to beat, and here are all the different rules. And one of the rules they gave me is I wasn't allowed to use more than 1 million clients to run the workload. 1 million. I thought, 1 million's a big number. So it turns out we can do that query in about 1/3 of a millisecond. Okay, so that's probably faster than most of the databases you guys use. This query is trivial, fraction of a millisecond. This one takes a little bit longer because it's returning a result set. It's about half a millisecond. So if you sum all those up, my math was right. It's less than a millisecond to run that query, the output of which runs that query, the output of which runs that query. All in under a millisecond. So let's just keep the math simple. Let's call it a millisecond. If one operation takes a millisecond with one connection, how many of these can we do in 1 second? 1,000? So if we've got one connection, we can do 1,000 TPS. So if we had more connections, in theory, we could have more than 1,000 TPS. Does that make sense? Okay. Any questions so far? Right.
Can you scale up to your 1 million clients?
So they gave me a throughput goal, and they said I wasn't allowed to use more than 1 million clients. So just think about this: 1 million clients, you've got 1 million. How many boxes does it take to run 1 million clients? Is it a process? Is it a thread? Don't care. How many boxes is it going to take to run 1 million clients?
Go for 1 million.
Okay, it would work with 1 million. Guess what? 1 million boxes, containers, VMs, bare metal, that costs a lot of money. I want to do this on the cheap. So I'm not allowed to use more than 1 million. I want to use way less than that because it's simpler for me and it costs less money. So any questions on that? So the point is, that's basic SQL. That should run on MySQL or SQL Server or DB2, pick your favorite database, don't care. It's just SQL. The update workload is different. It's a bit weird. You do a select. It's not a primary key select, but you can get because you're specifying 2 predicates in the where clause, you can get a unique row out of it. You do a select based on the current value of that row, and then you update that same table. Pretty simple, right? And for whatever bizarre reason, I'm not making this up, they do that 7 times on 7 different tables. From a data modeling point of view, that confuses me, but it's not my system. These guys make a lot of money. They know what they're doing. So the point is, their write workload is actually a combination of reads and writes. You're doing 7 selects, 7 updates, and a commit. Okay? So the system they have does a combination of the read and the write workloads. It does 60% of the reads and 40% of the writes. And this customer wants to go faster. I'll give you a hint. This is a telecommunication company. They're changing their infrastructure for 5G. It's not a fancier phone. It's actually completely changing the back end to make it do more stuff and make it go faster, make it more scalable.
So
Yep.
you're saying that it's all 7 of those things are the transactions, so you get
So for the write transaction, it's an ACID transaction. It does a select for the first table and update that first table, followed by a select for the second table and update. You do that for all 7 tables and then you commit. So there's 7 updates in that unit of work in that ACID transaction. Make sense?
Yeah.
Any other questions?
Why do we wait for the second table if they're completely independent?
Great question, because the unit of work, what makes sense for them for a business is all 7 of them have to all occur or not occur. So they want all 7 updates to occur as an ACID transaction.
Not the question of commit, but you can do them in parallel.
You can do them in parallel, but you have to guarantee that they all happened or none of them happened.
Yes, that's the synchronization. But the question is, why can't you do them in parallel?
We should have a deep and meaningful discussion on that over a beer. I know what you're talking about. I'm not sure that everyone else understands the implications of what you're talking about.
Is there any interdependency between these where the R2 has to wait for the result of R1?
Great question. I don't know the answer.
Okay. That would just explain why.
Yep. Yeah. I I literally don't know the answer. So I mean, I would say because, but I don't know. Okay, so the point is, the read workload was 3 different queries, which returned a result set. The write workload is reads and writes. So they have this system, which a bunch of you use every day. You probably don't know it, and they want to go faster. They want to go to 5G. So this company is sufficiently large that they don't care what the technology is. They don't care what the hardware is. They quite frankly don't care about the cost. This is their business. They want it to go faster. So money really isn't the issue. So they look at all technologies and they say, here's a competition, see who wins. And they do this all the time because it's their business. It turns out their current system is running on Oracle. Didn't know that. Fact. So this telecommunication customer uses TimesTen all over the place. Doesn't use it for this currently. They use an Oracle database. That was random. What they're fundamentally asking is, should they scale up or should they scale out? So when you scale up, you take your, the fastest, coolest, whatever CPUs you got, and you use lots of them, and you have a really big box. That's great, but it can only go so far. How many of you guys have heard of NUMA, non-uniform memory access? As you add more CPUs, it fights against you. You get to a point where adding more CPUs actually slows you down. Sound weird? It just does. Would you agree?
Yeah.
Okay. So the point being, if you have 1 or 2 CPUs, the cost of NUMA tends to be small. If you've got more, it gets expensive. So this company just happened to have Oracle Spark box. It could have been an AIX box or an HP Itanium box. It doesn't really matter. The answer's the same. So they had 4.27 gigahertz CPU. So the faster the CPU, the better, because it really helps. Those particular CPUs have a lot of threads, 64. Like these are more powerful than Intel Xeons. They just are. 2 terabytes of RAM. The more RAM that you can stick your database in, the faster it's going to go because there's less I/O. So that's a good thing. And so that's just a little pizza box. All the rest of it is storage. So they had lots of SSD, flash, NVMe, whatever you want to call it. Persistent memory storage, as fast as it gets. And then for backup, they had arrays of 10K spinning disks. They had lots of Gig Ethernet that happened to be running an Oracle 11G database. So that's the current system. They wanted to go faster than that. So think about it. When you're doing processing of data, you're moving data around. You're competing against a very fast CPU with a big L3 cache, lots of memory, and very fast disk. So if you're doing a distributed database, you have to beat the system bus. Okay? Does that sound scary or cool? Yep.
So were you able to determine whether you were CPU bound or memory bound on that problem?
Absolutely. I spent way too long figuring out that and making it go faster.
You need to know.
Yeah, no, absolutely. And those are the next slides. Perfect question. So the point being, this is their existing system. They were I/O bound. They had the choice of running single instance Oracle, rack, or Exadata. They could run any hardware they wanted. For them, for this workload, that was the best they had. So they tried all sorts of different technologies. They are huge Cassandra users. They've got lots of production Cassandra clusters. They've been using it for years. They know how it works. Most of those NoSQL databases I talked about earlier, they've benchmarked all those, and they brought us in. So MemSQL, to be frank about how serious about this is, MemSQL spent 6 months tuning this benchmark. So, they would be on site shooting the hell out of it because they wanted to win, because you get lots of money if you win the deal. I spent about 6 weeks doing it. I don't have 6 months. So you got pretty good hardware. The customer says to me, I want to go as fast as possible. So I go, cool. What cool hardware am I going to play with? They said, well, you're going to have some VMs running on CentOS, running on OpenStack. How many of you use OpenStack? Okay, it works, it's a private cloud, it's using Neutron, it's using NetApp for storage. They had the choice, like this company's large enough that they have server farms of NetApp, server farms of EMC, server farms of Ceph, so they had lots of choices. It turned out for what they were doing, NetApp was their fastest thing. So the fastest hardware they could find, they said the shape of the VM, you've got 32 cores, it's only got 64 gigs of RAM. So if you do in-memory database stuff, the more data you stuff in memory, the better. Because if you can process it all locally, you don't need to do a network hop. If you can process it locally, you're going at CPU speeds and you go fast. So in their infinite wisdom, they said, your shape is 64 gigabytes because that's the perfect size. I think it's a ridiculous size, but that's what they gave me. So that's what they had. So any guesses on which was fastest? So to be very clear, when I went into this, I didn't know who would win. Did not know. Any guesses on who won?
The dedicated hardware, the one on the left.
Good answer. Any other answers? Okay, so I'm going to show you the answers. I'm going to talk about some of the challenges and then some of the approaches we got to make things go faster. So, the existing production system does about 240k transactions per second. So, a transaction per second is 60% of the time a read, 40% times of a write. So a transaction is either one or the other, but on average 60% of the time it's a read. So it's blended, it's a weighted average. They were IO bound on that machine. I don't know what throughput Cassandra gave me. They laughed and they said it wasn't fast enough, it had negative scalability. So Cassandra can scale really well. For what they were doing, it was so write intensive that when they added more nodes, it just became more of an IO bottleneck. So it actually, over a certain point, had negative scalability. It was nowhere near the 240. MemSQL spent 6 months, they did 168k. I came in and I said, what do I need to do? What's my benchmark goal? Because if you don't have a benchmark goal, you will work forever. So they gave me a number, I just had to beat that number. They gave me a number of 300k, I did 304, I said we're done. But that's not actually what happened. A couple of days after they gave me this challenge, I said, I got 11 million per second, I'm done. And they said, no, you don't understand. How did I do that? Did I cheat or was I smart? I got some big machines, they weren't bare metal, they were VMs, but they had lots of memory. And because they had lots of memory, I could stick all of the data in the machine. So logically, it'll all work on one machine. But because it's a scale-out database, if I had many machines, I could do more stuff in parallel. So they gave me some Python code, which I didn't touch, I didn't quite frankly understand. They gave me some Python code for Oracle. I ran that on TimesTen, it worked unchanged. Because the data was all local, there was no network hops. Because there was no network hops, it was going at CPU speed. By having lots of connections on lots of machines, I got linear scalability. 11 million, whatever those transactions are per second. Cool. They said, no, you're not allowed to do that. The actual data is bigger than that. And your actual machine has only got 64 gigs, which was quite frankly not big enough to fit the data in. So that forced me to spread the data over many machines. When you spread the data over many machines, you have to do network hops. Network hops are evil, they slow you down. Okay, so just what the numbers are doesn't really matter. The point being their throughputs. MemSQL was on site for 6 months. They had Cassandra experts and data stack people on site. So we won the throughput. The question is, how did we do it? So I've got some questions for you guys. These questions aren't for my product. Think your SQL product. Question 1. If we're going to select star from a table where primary key equals some value, so we're doing a single row lookup on one table, and we're going to use client server. So there's going to be a network hop from my client machine to the server machine. The question is, how many network round trips it is? The answers are 1, 2, 3, lots, or it depends. So who knows the answer to the first one? Yep, sir. Just one? Just one?
1, 2, and 1 back.
So maybe 2? Do we have any other considerations? How many? Okay. Which API are we using? Is it JDBC? Is it ODBC? Is it OCI? Is it Node.js? I would argue it doesn't matter. When you're doing SQL, you do an execute, you fetch a result set, and you do a close. 3 different operations. Is that 1 network round trip or 3? 3? Okay, I'm messing with you. It depends. Depending on your database, they can optimize it to do it all in 1 network round trip, logically. If you're returning a single row in the result set, it can know to do it in one, so the execute, fetch, and close all in one go. Okay? Logically 1. I'm saying select star. If I've got a really wide table with lots of clobs, that could be a lot of data. So logically it's 1 round trip, but physically it could be many network packets, because it depends on how much data is being returned. Does that make sense? Okay, next one. Instead of returning a 1 row, we're returning between 10 and 20. So we're getting a result set with your bunch of rows. Is that going to be 1 round trip, 2, 3, many, lots?
1.
It can be done in 1. If you've got a good database and you tune it, it can be done in 1. In general, you can't do it in 1. If the result set was large, it's not all going to fit in 1 packet, so it could take many round trips. Okay, that seem reasonable? So we're talking about the easy stuff, from the client to the server. Okay, next one. We're doing an update against a single row. How many round trips? 1? Seems reasonable. We're doing an update where we're updating lots of rows. How many round trips? Doesn't matter. It's irrelevant. It's irrelevant. I'm not talking about TimesTen Scaleout. This is true for any database. If I'm doing an update statement, which, say it's updating 1 million rows, how many client-server round trips is it going to take?
So are you doing the commit over here or not?
I'm not doing the commit. Okay?
Yeah, it's just 1.
Correct.
You
It
get
can
to
be.
tell the thing, go do your job.
Yep. It can. From the perspective of client-server, it can be done in 1. What say we were doing a select with a join of 4 different tables? I haven't specified the where clause because there's lots of conditions. Just imagine it's not giving a Cartesian product. Just imagine it's a good join. How many client-server network round trips is that going to take, logically?
For which one? Number 5?
For number 5. Okay, I've got 1. Any other answers?
Again, it depends on your result set. If you can carry all the
Absolutely.
results.
Imagine it's returning a single row.
Oh, okay.
So in theory, you can do it in 1. This is the easy peasy bit. This is the client server hops. This is now running against a distributed database.
Yeah, that's inside.
I don't care what the distributed database is. If the database is spread over many nodes, sorry, if the rows in a table are spread over many nodes, there are going to be network messaging happening on the server side. It's got nothing to do with the client server, it's independent. So for instance, when we did an update and we updated 1 million rows, it made client server be a single message, but it could be, is it 1 message, 10,000, 1 million? You don't know, it depends. Does that make sense? The point I'm trying to make is when you've got a distributed database and you're doing, quite frankly, trivial SQL, network messages will occur. And the more complicated the SQL and the more concurrency you have, the more messages you're going to have. So messages, client server, plus server-side messages, times the number of clients can equal a lot of messages. Does that seem intuitive? So, the point I'm trying to make is network hops are evil. Okay, any questions on that? Okay, just doing a quick time check. Okay, better hurry up. So, scalability challenges. Dennis was saying, you know, to go fast, you co-locate data. If you're doing a join with all the data on the same node, it's going to go faster. It's going to go at memory speed, it's going to go at CPU speed. If your table's got the data distributed across them, you're going to have to do network hops. How many network hops depends how smart your database is, basically. When the data is huge and the VMs are small, you're going to get more distributions. So my customer wanted the system that was as fast as possible, and they gave me basically the crappiest hardware they could. They gave me lots of, you know, not very much memory, which forced network hops. The updates, you don't know where the data is. Client server round trips we've talked about. Not much memory we've talked about. I like OpenStack, it works. It turns out when you really stress it, the neutron, the networking services, what I found at this particular customer, the network was the bottleneck. So I'm doing far more networking hops than I wanted, and they had a non-optimal networking stack, all of which equals bad, bad, bad. Okay, any questions on that? So those were the challenges. Next slide, I'm going to go over how I address those challenges. So there's not a lot of rocket science here. First of all, determine the best distribution clauses. What does that mean? With a distributed database, how is the data spread? So you've got rows in the table. How is it spread over machines? It depends. That's up to the database. With my database, there's 3 ways. You can distribute by hash, actually a consistent hash. You can collocate it locally by reference, or you can duplicate the data everywhere. So the question is, if I've got 3 choices and lots of tables, how many combinations of distribution clauses and tables can I have? The answer is lots. If you have to load data and query it to see how fast it goes, it takes too long. So I'm lazy or smart, depending on how you look at it. We've got a thing called a distribution advisor. You give it a table, you give it a workload, and you say, what's the answer? And it will recommend what the distribution clause is for that workload. Obviously, mileage will vary. If you give it a different workload, it may not be the best answer. But the point is, you give it a workload that's representative. Is that one query, or is it 10,000 SQL statements? If you give it a representative workload, it should tell you the best recommendation for the distributions. Make sense? Next thing, indexes. In-memory databases are cool. In-memory databases are fast, but they're not magic. If you're doing full table scans, you can probably get a faster answer if you have an index. So I needed about 22 indexes. I'm lazy. I just ran the workload, and the index advisor literally generated the indexes for me. Prepare and bind SQL statements. Who knows what that means? Okay, cool. How many of you use SQL? How many of you know what prepare and bind means? Okay, I'm trying to give you a guilt trip here. If you don't prepare and bind SQL, you do dynamic SQL. When you do dynamic SQL, you're making the database do work. It has to parse the SQL to say, is it syntactically correct? It has to figure out, is it semantically correct? It has to figure out the data types. Once it knows all that, it can come up with a query plan. Once it does all that, it can actually do some work. So that's a lot of work that you want to do once. If you use dynamic SQL, if you don't prepare and bind, you do that all the time. Okay, it's evil. Prepare and bind your SQL. Check your explain points. So one of the biggest tricks I did for this distributed database is I used a trick from 20 years ago, stored procedures. In one network hop, I can do many network statements because the SQL is running on the server, not on the client. Not rocket science, but it works really well. So if you think of all the different queries I had and the number of network hops it could take, you chain all those up, that's a number. It was 27 in my case. If I can replace that with